When a plane harmonic sound wave travels through a fluid medium, it sets its particles into a pattern of motion. The particles acquire both kinetic energy and elastic potential energy. The easiest way to see this is to estimate the time averaged energies per unit volume of the medium. We will start with an estimate of the average kinetic energy stored per cc of the medium due to the passage of the wave. The kinetic energy per cc is the usual expression half mee squared with ρ naught v naught as the mass of the fluid parcel and u being the particle velocity. The kinetic energy per volume is independent of the volume of the parcel as it scales linearly with the volume. To get the time average, integrate over time and take the average. The integral contains the square of a sine function whose average value is half. This leads to the factor of a quarter in front. Is the amplitude of the particle velocity. Make use the expression of the particle velocity obtained near the end of the previous lecture to get the expression for epsilon k, the symbol for the time averaged, per unit volume quantity. The wave compresses and stretches fluid parcels in its course. Energy is stored as pdv work in the medium. We specialize for the case of adiabatic transport. Since the adiabatic bulk modulus is constant, dv is simply related to the dp. Working out and rearranging the result, we have an expression for EEU which is also linearly proportional to the v0. Having got the per unit volume value, we now calculate the time average. Taking average of PE squared is like taking the time average of the square of any sinusoid in that it introduces a factor of a half and the square of it amplitude PM squared. Using the relations obtained in the last lecture, we get the final expression for epsilon u. In the next slide we are going to see that the time averaged KE and the time average PE are actually the same. Screen 4. We make use of the sound speed, bulk modulus relation and the dispersion relation for plane waves to see that both the time averaged kinetic and potential energies stored per unit volume of the medium are actually the same. This means that the total time averaged energy density is just twice the value of any of these densities. The expression can be transformed in terms of the pressure amplitude also. It is important that you would be able to establish these simple relations on your own. To this end, you would find the summary page at the end of the last lecture to be quite useful. We have found that the kinetic energy is proportional to the square of the particle velocity, where does the potential energy is proportional to the square of the instantaneous pressure, and these two quantities always oscillate in phase. Thus the kinetic energy and the potential energy always reach their maximum and minimum together. In harmonic oscillations these two are always separated in phase by 90 degrees. Think about the energies in the capacitor and the inductor in LCR circuit for the potential energy and the kinetic energy of an oscillating pendulum. The conclusion do not change if we consider spatial variations instead of temporal variations, as both of them are sinusoidal although with different but related periods. That is, if we look at the medium, we find that there are regions of very large energies separated by regions of very low energy. We have found the average energy stored per unit volume. This energy is carried by plane waves into the medium. We can find the intensity of the wave which passes through the medium. The intensity is defined as the amount of energy transported across the infinite plane wave front per unit area per unit time. With epsilon as the average energy, the energy transported through a part of the wave front of area S is epsilon times S times delta x over a volume of size Es delta x. Finding out the rate transmitted per unit area per unit time, we arrive at the expression I equals epsilon times Cs, where Cs is the sound speed. It can also be written down in terms of the pressure amplitude as shown below in blue color. The intensity can be expressed in various ways. We can write it in terms of the RMS value of the excess pressure by remembering that peak values of sinusoids are square root 2 times their RMS values. One important result is that we can write it as a product of the RMS values of excess pressure and the particle velocity. The decibel we define in terms of intensity and the decibel defined in terms of pressure differ by a factor of 2, and in the screen we find why it is so. The reason is simply that the intensity being proportional to the square of the pressure level donate a factor of half from the logarithmic ratio of the intensities. From this expression we immediately know why the word decibel is used. It is 1/10 of the bell, which is the unit of sound power level named after Alexander Graham Bell and is simply the logarithmic ratio of the intensities to the base of 10. The bell is the natural unit for logarithmic ratio of intensities. In this example we try to find the gain in decibels. We find that if the second intensity is higher than the first by 3 decibels, the log of 2 to the base 10 frequently appears in calculations and is easy to remember. The RMS speed of air molecules is related and nearly same as the speed of sound in a fluid, and the reason is that they differ by a factor which is nearly 1. The factor depends inversely on the square root of the adiabatic index. Often the sound speed, which is easily measured, is taken to be a first estimate for the particle velocities even in mediums other than an ideal fluid. The speed of sound may depend on several factors, but they do not depend separately on the pressure and density for ideal gases. The reason is simple: for ideal gases the sound speed depends on the ratio of the pressure to the density and therefore always varies in step. The atmosphere is not an ideal gas system, however, and as a first approximation, the sound speed does depend on pressure in the atmosphere. An increase in pressure causes an increase in sound speed, although not so much to be observable under terrestrial conditions. Even for an ideal gas, the speed of sound does indeed depend on the temperature. The nature of variation is indicated in the first expression that appears to the right of the vertical separator on the page. In the expression, T is the temperature in the Celsius scale, not in kelvins. Proof of the formula follows. The point in converting to the Celsius scale serves to illustrate the fact that the change is slight but significant. Exercise: look at the data given in the following image. Can you use the formula for sound speed obtained above to predict/explain the data? It would be good if you write a few lines of Python to check the results. You won't even have to import any module to check these data. Presence of water vapor increases the sound speed. Think about replacing some nitrogen molecules with water molecules. As long as the number of moles stays same, any ideal gas system would have the same pressure. In this case, therefore, the pressure remains more or less the same. But the lighter water molecules does make the density go down, and, since the sound speed depends inversely on the square root of density, it goes up. Changing the pitch affects the speed for ultrasonics, and large amplitudes make the speed of sound change in shock waves. They do not affect audible sound to any perceptible degrees, however. This concludes our lecture on acoustic sound waves.